Hello, everyone, and welcome to this session 6B on emerging technologies. I am very happy to welcome you to the VLSI conference in 2022. We will start the session with an invited talk on emerging memory based on processing in memory architectures for low power deep learning. This talk is going to be presented to you by Fan Chen. She is currently an assistant professor in the Department of Intelligent Systems Engineering at the Indiana University Bloomington. Her research interests include computer architecture, emerging and volatile memory technologies, and hardware accelerators for emerging applications. Dr. Chen is a recipient for the 2022 NSF Faculty Early Career Development Program Award, the 2021 Service Recognition Award for Great Lakes Symposium on VLSI, the 2019 Cadence Woman in Technology Scholarship, and the Best Paper Award and the PhD Forum Best Paper Award in 2018 Asia and South Pacific Design Automation Conference. I would like to thank Dr. Chen for providing us this invited talk, and I will hope you enjoy the video.
In this work, I will present our recent research on deep learning acceleration by using emerging memory technologies. In our daily life, we see deep learning or machine learning being used everywhere. It has become the cornerstone for many different kinds of applications. Essentially, a deep learning model can be viewed as a mathematical model implemented by many layers. The deep learning model is really trying to map an input to a target label by optimizing a predefined loss function. We perform this optimization many times through the so-called training process. And after a model is developed, we will be able to deploy it onto a device to perform a test, or what we call inference. So particularly for deep learning models used in image processing areas, over 90 or even 99% of the computation is really dominated by the convolutional or fully connected layers. Here we call them conv or FC layers for short. So naturally, in most of the DNA accelerators, conv and FC layers are really the target for hardware acceleration. Okay, so here I show you all the three computing phases involved in deep learning processing. So for deep learning inference, we only perform this forward inference pass to get the results. The computation here are between the input feature maps and the kernel weights, which are essentially a lot of multiplications and accumulations. We call those MAC for short. For the training part, we also need to perform two backward pass. One is called the arrow backpropagation. The other is called the partial derivatives. The goal for these two passes is really to figure out what is the updating value so that we can just update our parameters in the next training round. Okay, I show you the numbers of the parameters number of the parameters and number of the operations for some recent deep learning models. You can see they are really computation and memory intensive, even for just a single forward pass. If you consider training, this is essentially a 3x more computation. Okay, so however, for the current general purpose platforms, they basically has this kind of like von Neumann architecture. The mean memory, in fact, becomes a critical constraint in latency, in bandwidth, and also in energy. So to address this, we use like emerging memories to realize a new architecture which can perform the computation in memory. Okay, so in this table here, I compare the Google TPU with a PIM, we'll call it process in memory, a PIM design. So please note that even for Google TPU, they are already optimized accelerator for deep learning processing, but still they suffers from the von Neumann bottleneck caused by the long access latency and high energy consumption to the off-chip main memory, as I highlighted here. So one thing I want to highlight is you see that the PIM design enables us to realize a non-von Neumann architecture, and intuitively we can think that if we correctly use this architecture, it can bring us impressive savings. Okay, So generally for PIM designs, they basically all follows kind of like the general mapping scheme as I demonstrated here. The kernel weights are really transformed into a weight matrix, and the input feature maps are reorganized into the input vectors. After this transformation, the computation can be efficiently mapped onto such kind of like crossbar structure, which basically are implemented by different kinds of emerging memory technologies. You can see the input values are shared across multiple rows, while the partial sums are accumulated along each column. So this, the typical size of those crossbars is like 128 times 108, or even 256 times 256, which really gives us a very high parallelism compared with the single MAC operations in CMOS-based design. Okay, here I also explain the general PIM architecture. So at the circuit level, it requires like a analog digital conversion. We have DACs and ADCs to realize what we call a vector matrix multiplier. We call it VMM for short. And for each processing energy, PE, it contains multiple VMMs and also a buffer to cache the temporal data, and also several units required for like nonlinear functions or output aggregation, so on and so forth. At the top level, the PEs are connected through an on-chip connection. It needs a controller which deals with how to map the DNA accelerations onto the PEs and also controls the computation flow. And of course, we also have memory interface to communicate with the host CPU. So by following this kind of PIM design concept, next I will explain 3 of our recent works. Okay, so due to the time constraint, I will just briefly focus on the design highlights. For more details, please refer to our related papers. Okay, in the first work, I'm going to introduce our work, which is called ReGAN, which is really a training iterator for the generative adversarial networks. So the number one question here is why we choose GAN model and what is it, right? So GAN is really a training framework for unsupervised learning, which has quickly become one hot research area ever since it was proposed in 2015. But the problem here is, as you can see here, in the GAN framework, it contains 2 deep neural networks co-trained together. We call them generators G and discriminators D, respectively. The co-training of these 2 deep learning models is really time and energy consuming. Okay, so the key idea in our work is really to follow the previous described mapping schemes to map the computations onto the ReRAM crossbar structure showing on the left. And then we propose to perform the training in the pipeline fashion. So as I just demonstrated in the right part here, basically you can see we divide the on-chip ReRAM crossbars into 3 parts, each of which respond for just one computing phase. And then in this case, when training the data is fed into the accelerators in a batch, the processing can be pipelined and roughly provide us a speed up factor of the batch size B. Okay, so on top of those pipeline structure, we further proposed 2 techniques to improve the efficiency. The first technique is called the spatial parallelism, which is really based on the observation that these 2 training phases, as I shown here, they are independent, but they shares, but they both runs on the discriminator model. Therefore, the idea here is we just duplicate this discriminator for 2 copies, and therefore these 2 training passes can be performed in parallel at the same time. Okay, so in this way, the total latency is only the latency of the spatial parallelized models, because part of this like shared part will be had by this kind of like in parallel processing. Okay, the second technique is called computation sharing, which really refers to these two training passes showing in this top finger here, top and bottom finger here. So as you can see, these two training passes, they are distinguished from the definition of the loss function, right? And therefore, they have different back propagation data paths, but the forward paths are exactly the same. So with this observation, we propose to co-train the D and G by duplicating the memory for the intermediate computations. In this case, the training of the D and G share this like forward paths, and only the two backward branches are computed in parallel. In this way, we reduce both computing latency and hardware requirement. Okay, so we evaluate our design against the previous works on different benchmarks. So basically, you can see we can achieve roughly 2 orders of magnitude improvement in terms of both performance and energy savings. Here, I summarize the ideas and the key solutions in this work. Okay, so the second piece of work is called Marvel. First, let me explain the motivation of this work. We know that our ReRAM-based designs, like the RayGun I just explained before, can process the DNA models in a pipeline fashion. But however, the computation happened in ReRAM crossbar essentially in analog domain. So we will need ADCs and DACs for this kind of like analog and digital conversion, which incurs large area and power overhead, as I shown in the right finger here. So also we need input and output SRAM buffers and large EDRAM global buffers. They also consume a large portion of the area and the energy. Okay, so to address these problems, we are considering to improve the area efficiency as well as the power efficiency by using the advanced 3D integration. We take this 2D ReRAM-based design as our baseline. We first partition the 2D designs into 3 layers, as I'm showing you here. Particularly, you can see I place the ADCs and DACs on the bottom layer because it will be more close to the heat sink. The first question will be, what kind of 3D connections can we use, right? So we consider 3 candidates. Here, the TSV model is, the TSV stands for the conventional through-silicon vias, and the mini TSV is an aggressive TSV model with about 60% diameter reduction. The ILV stands for the advanced interlayer vias, which has substantially reduced the diameter. Okay, so in this baseline design, each crossbar needs to be connected with 128 DACs as well as other peripheral circuitries. So to meet this connection density, we find that only this ISV model meets our requirement, so that we adopt this model in our baseline 3D design. Okay, so we now expect to improve the power efficiency with such kind of 3D design, right? But the simulation results shows here that actually it increased the power consumption by more than 10%. So the reason is that the peak temperature of the chip has increased to 103 centigrades due to the increased power density in the bottom ADC layers. So this increased temperature caused the retention time of the EDRAM buffers decreased by 2x, as I show you here in the right figure, and hence it results in a 2x more refresh energy. Okay, so to reduce this power consumption in the bottom ADC layers, we propose to replace those CMOS-based ADC designs with the recently proposed carbon nanotube, CNT, CNFET-based ADCs. The CNFET-based designs have smaller size, but reduce the frequency as shown in this table here. So our experimental results shows that with such kind of replacement, the power consumptions can be reduced. However, it also degrades the performance due to those slower ADC frequency. Okay, so to match the performance of the 2D baseline, we inevitably have to construct multiple ADC layers. So thanks for the low temperature fabrication property of thin fight. They are ideal for the 3D integrations. So we first explore to integrate 2 layers of those like 20 megahertz ADC unit. And moreover, we also performed a design space exploration by integrating like a scaled 10 megahertz ADC designs. The parameter of both ADC candidates are showing in this table here. Okay, so the results report here, basically you see the green bars show the results of the 2-layer 20 megahertz ADC designs, and dark green bars shows you for the 2-layer 10 megahertz ADC designs. You can see they both match the 2D baseline performance, but only the M3D designs favors the 10 megahertz design in terms of both power at the system level. So therefore, in the following evaluations, we only report results by using this like 10 megahertz ADC units. To further improve the error efficiency, we also replaced the input buffers with SIMFAT-based SRAM buffers. Also, we replaced the EDRAM buffers with the 3D cross-point STT-RAM based buffers. Here, I show you the overall architecture of a 3-layer Marvel design, which consumes only like 13.3 square centimeters chip area and also only a 14.5 watt power. Based on the experiment results, you can see we show our design achieves 4.5 times improvement on performance per watt. Okay, to sum up, we just showing all the key informations in these slides. Next, I will quickly go through our very recent work on FiFET-based DNA training actuators. So basically, recall the training in the conventional backpropagation-based designs. You can see we want to store all the intermediate data since they will be used in the backward pass, which not only increase the memory requirement, but also makes the training parallelism very challenging. So the idea is here we find that the recently proposed direct feedback alignment-based algorithms can give us the potential for parallel layer updates. And also we see the FiFET devices has some like very favorable features which can enable us to design a ADC-free accelerator. So we just propose a FiFET-based process engine, also a FiFET-based random number generator, also a FiFET-based ADC, and also we just implement all the units within a pipeline within a new pipeline. Okay, so here I show you the overall architecture. The highlight here is we have a FiFET-based random generator, which is essential for the DFA-based design. Also, we have a FiFET-based ADC unit here. Basically, I show you the random generator results and also the ADC results here. And also this is the overall pipeline. So you can see we can maintain the roughly the accuracy compared with the simulation results, and also we show you a significant improvement in terms of both performance and energy. Okay, so I summarize all the key information in these slides here. And besides all the works I have been proposed, I also explored like how can we support new models, new applications by using those like kind of team-based design concept. We also did some explorations at the algorithm level and as well as the system level. Okay, so thank you for your attention. If you have any questions, feel free to contact me by sending me an email.
Sorry, I will start again. After this very interesting talk, I would like to lead you on to the continuation of these sessions, and we will go forward with the regular talks. And at this moment, I will introduce the threshold voltage modeling of negative capacitance double gate TFETs, work presented by researchers in Cochin University of Science and Technology.
Hi all, myself Shika from Cochin University of Science and Technology. The title of the work is Threshold Voltage Modeling of Negative Capacitance Double Gate Effect. My co-authors are Rekha K. James, Anju Pradeep, Sumi Baby and Jobimol Jacob. I'll be giving you a brief overview of our work in the introduction part, then the schematic diagram of the device and the numerical simulation, then the model development, and finally the results and conclusion. Well, we know that MOSFETs are having extremely high off-state current, and also we cannot reduce the subthreshold swing below 60 millivolt per decade. And to face this power crisis, steep slope transistors have evolved, and the most prominent one among them is tunnel field effect transistor, which is having the current conduction mechanism as band-to-band tunneling. It is having extremely low off current and also subthreshold swing less than 60 millivolt per decade. But the drawback of this technology is its on current is not as promising as that of a MOSFET. So various topologies are proposed so far to increase the on current without sacrificing the other performance parameters. And the most recent topology is negative capacitance TFET. Negative capacitance is a unique property of ferroelectric material which provides voltage amplification and subthreshold swing reduction. So in case of an NC FET, the ferroelectric material is placed in between the gate metal and the gate insulator. So the gate stack is having a gate metal, a Fe layer, and an insulator. So with this topology, the on current gets improved and the subthreshold swing gets reduced. A very important electrical parameter for a solid state device is the threshold voltage. In case of TFET, we have two threshold voltages, a gate threshold voltage and a drain threshold voltage. But in our work, we have modeled only a gate threshold voltage. So this work is an accurate gate threshold voltage modeling of a negative capacitance double gate effect. And this model is very simple. The significance of this model is in conventional method, we have to extract the threshold voltage from the drain current. And the drain current modeling is a tedious task. Firstly, we need the surface potential model. And from that, we have to take the derivative to get the electric field. And using the electric field, you have to solve the Keynes equation. And that Keynes equation will be giving you the tunneling generation rate and then taking the volume integration. And this volume integration is a very time consuming thing. To get the drain current. And from the drain current, we can extract threshold voltage. So this is the typical method, it's a conventional method. But in our paper, in our work, we extracted the threshold voltage directly from the surface potential. And it is very accurate as that of the other accurate methods. The study includes a comparison between the conventional TFET, that is a non-NC TFET, and the proposed NC TFET. Also, it includes the dependency of ferroelectric thickness and dielectric constants on the threshold voltage. Well, this is the device structure of the NC double gate TFET with a channel length 100 nanometer, channel thickness 10 nanometer. The insulator material taken here is, we had taken two insulator material for this comparison, for a comparative study, silicon dioxide and hafnium dioxide, and each of thickness 3 nanometer. The ferroelectric material taken here is silicon doped hafnium dioxide, which is CMOS compatible and shows ferroelectric properties even in a 3 nanometer thick layer. Its thickness is 5 nanometer. Then the device is homojunction silicon TFET with its source being heavily doped P-type with a value 10 power 20 per centimeter cube as a concentration. Its drain is heavily doped N-type with 10 power 19 per centimeter cube, and the channel is 10 power 16 per centimeter cube. The work function of the metal is 4.4 electron volts. So in a normal TFET, we can directly simulate it using TCAD, two-dimensional TCAD. But in case of negative capacitance TFET, due to the unstable nature of negative capacitance, we cannot directly depend on the TCAD for a numerical simulation. Instead, we need to consider one-dimensional Landau-Kalanoka equation and the TCAD for the simulation purpose. A combined numerical simulation is required. So how to do that? We have a structure, metal ferroelectric insulator semiconductor. That is the proposed structure. But as I told you, we cannot directly simulate it using TCAD. So we are introducing some modification for the structure. We introduced an intermediate metal layer in between the ferroelectric and the insulator. So the structure will be MFMIS. And the MF part can be solved using 1D LK equation. And the MIS structure can be directly solved simulated using a TCAD. And another important feature of these two structures are they exhibit property dissimilarity less than 10%. So we can easily compare. We can say that if you have an MFMIS structure, the property will be almost similar to that of an MFIS structure. So we can go for the simulation. Equation 1 gives the ferroelectric drop, the voltage drop across the Fe layer, where alpha Fe and beta Fe are the LK parameters. Its values are given in equation 2. Q is the charge density, where alpha Fe in the term, it is having a negative term. So this VFE will be always negative. And EC, TFE, PR are the values, are the Cauchy field, thickness of the Fe layer, and the remnant polarization respectively of the Fe material. Then we can write the gate voltage in terms of the voltage drop across the two layers. That is VFE plus VS. VS is a voltage drop across the semiconductor, or we can say it is the interface potential. So as I told you, VFE will be negative. So if you provide a 1 volt gate voltage, the input to the semiconductor will be greater than 1. That means there is a voltage amplification, even in the absence of an amplifier. With just a Fe layer, in its NC domain, you'll be getting a voltage amplification. Now moving to the model development. Firstly, we need a surface potential model, as I told you. So for the surface potential model, we are applying Gauss law, and in the figure, in this device structure, you can see a Gaussian box. It is where we are applying Gauss law. Equation 4 is a Gauss law, and ESF is the electric field at the interface, at the top gate interface. C stack is the gate oxide capacitance of the entire gate stack, which includes the capacitance of the ferroelectric material and the insulator capacitance. COX is the insulator capacitance. Eta is the channel spreading parameter, which is its value taken here is 1. Epsilon SI is the semiconductor, is the silicon permittivity. TSI is the silicon thickness. Then VGS is effective gate voltage. Psi SF of X and psi SD of X are the surface potential of the top and bottom gates respectively. NCH is the channel concentration, and Q is the charge, electron charge. The equation 5 is the gate oxide capacitance, and the reduced expression for the surface potential is given in equation 8. Once we apply the electric field displacement continuity property for this, for the Gauss law, we'll be getting equation 8, where alpha square and beta values are given in equation 9 and 10 respectively. The general solution can be written as in equation 11, where A and B values can be obtained by applying suitable boundary conditions, which is given in equation 12. So the values for A and B will be obtained as in 13 and 14. So now with this, if you substitute the values for A and B in equation 11, you'll be getting the surface potential. That is the surface potential model. So from that, you can derive the threshold voltage, and this is nothing but based on the physics-based definition of threshold voltage in ferroelectric material. in a TFET. So gate threshold voltage is the gate voltage at which the energy barrier narrowing saturates with VG, with the gate voltage. That means in TFET, everything is related to band-to-band tunneling. So here, the definition is gate threshold voltage is the gate voltage at which the energy barrier narrowing saturates. That is, if you further increase the gate voltage, the energy barrier narrowing you cannot find any promising change in the energy barrier. The narrowing will be almost saturated. So that gate voltage is the gate threshold voltage. And if you substitute X is equal to WB, where WB is the saturated barrier width, and psi SF and the surface potential as VDS plus VBD. VDS is the drain voltage and VBD is the built-in potential of the drain side. And VG if you replace VG with VTH and substituting these values, you'll be getting equation 17. That is the threshold voltage model, where the constants are given from we'll be obtaining the constant from equation 18 and 19. Well, these are the results. Well, figure 2 shows the energy barrier width variation with gate voltage for a conventional double gate TFET and the proposed TFET for two different values for high K and low K materials. As you can see, for a high K material, it's obvious that the barrier width will be very low because of the higher capacitance of the dielectric material, of the hafnium dioxide. And as you see, as the gate voltage increases, at the initial part, both the conventional double gate TFET and the NC TFET are having exactly similar barrier width. But when the gate voltage increases, you can see a deviation from the values. It is due to the voltage amplification. As the gate voltage increases, the voltage amplification also will be more in case of an NC. Well, this is the extraction procedure, the VTH extraction from the simulation, and it is done by the transconductance change method. So according to this method, the derivative of the transconductance gives the threshold voltage, and it is nothing but the gate voltage at which this change in transconductance will be a maximum, and it is shown in using this arrow. You can see the threshold voltage is the peak value of the curve. And now the variation of threshold voltage with drain voltage for epsilon equal to 22 for a high K material, for a conventional and the proposed TFET. And you can see as the drain voltage increases, it is obvious that the threshold voltage will be more for a conventional double gate TFET, because in an NC TFET, the voltage amplification, due to voltage amplification, the threshold voltage will be low. So as the threshold voltage increases, as the drain voltage increases, the threshold voltage also increases. And you can see the model and the simulation results are exactly matching. A very slight deviation is there, or it is almost matching. And this figure shows the variation of threshold voltage with Fe layer thickness for a high K and a low K material. And as the thickness increases, the threshold voltage decreases, because the reason is the same thing. The reason is the voltage amplification itself. As the Fe layer thickness increases, the voltage amplification will be more. As a result, the threshold voltage will be less. Here also you can see a good matching, good agreement with the simulation results. And this table is the validation of the proposed model for varying dielectric constants. So as the dielectric constant value increases, the threshold voltage value decreases, and you can see the comparison between the model and the simulation results. It is almost matching. Well, let me conclude. an accurate simple threshold voltage model for NC double gate TFET is proposed in our paper. It compares the threshold voltage of a conventional TFET and an NC TFET. We also studied the threshold voltage for varying FE thickness and dielectric materials. The future scope is the drain threshold voltage model for NC TFET based on the definition, physics-based definition of drain threshold voltage in a TFET. These are the references. Thank you.
Thank you for your presentation. And I would like to ask you two questions, actually. First one, it is a very interesting method that you're proposing to model the threshold voltage. Would you say that it's easier or more complex to include any kind of deviation process variability in your model than in the classical approach?
Sorry, can you repeat it?
Modeling the process variation effect on the threshold voltage, would it be easier or more complex with your approach compared to the classical one?
So far, we had done some dual material gate modeling also. In that also, we know that in case of TFET, the source to channel tunneling is a major contributor of drain current. So I think it won't affect much, even if you are going for a dual material or another structure, complicated structure. Just the source and channel tunneling is the major thing. So I think it won't affect much if you are going.
Thank you. Thank you very much for your presentation. Thank you very much for participating in the conference. And I would like to move to the next paper, which is, yes, the next paper. It's on design optimization using symmetric and asymmetric spacer for 14 nanometer multi-FinFET and mid-band 5G applications. And this work is developed by researchers in IIT Rourke. Thank you. You have the floor.
Hello everyone, my name is Jyoti Patel and I'm going to give presentation on the topic of design optimization using symmetric asymmetric spacer for 14 nanometer multi-fin tri-gate FinFET for mid-band 5G applications. Outline of this presentations are introduction, device structure and calibration, small signal equivalent circuit, results and discussion, comparison of RF parameters, and then conclusion. We all know that mobile data traffic is projected to rise 53% each year into the foreseeable future. And this increase in data, we need very high frequency spectrums. And 5G has capability to accommodate more data than the 4G without compromising the data rate. And to enable this high data rate transmission, 5G uses frequency band above 24 GHz. So for this, it also requires a highly scaled low power devices for the optimized battery life. 5G can be the candidate, such FinFET can be the candidate device for the 5G application, as it is having the faster switching time, better gate controllability because of the multi-gate, higher current density with some structural modifications. It does also provide very high Fmax with low noise performance, even for the sub-6 GHz 5G applications. So in this slide, we can see the device structure and the calibrated results. So the left-hand side showing the single-fin tri-gate structure for the channel and 20 nanometer, which is calibrated with the already reported experimental data into the paper 2014. So we have simulated these results in TCAD and calibrated it with experimental data for linear as well as in the saturation region, and they match quite well. So moving forward, we have increased the single fin device for the multi-fin structure, and we have taken the fins, increased the number of fins to the 3 fin, and we haven't increases further number of fins because increasing the number of fins also increases the gate resistances. And there are much parasitic elements inside the device, which can be seen here in the small signal equivalent circuit model of the multi-fin device. So there are the RGS and RGD, which are the distributed resistance for the gate to source and gate to drain. And similarly, it is also having, for each number of fins, there are multiple gate to drain and gate to source capacitances in parallel. So N is generalized, like denote the number of fins basically, which is 3 here. These intrinsic parameters can be determined with the small signal model using Y parameters. So all these intrinsic parameters can be back calculated with the Y parameter achieved from the TCAD. All the parasitic elements basically deteriorate our device performance. So improve the device performance for the high frequency side. We have did some device level optimization. For this, we have introduced slight asymmetry in the spacer. So the first one structure, which is A, is showing in the left hand side, showing the drain spacer and source spacer with the equal length of 10 nanometer. Then we have introduced the asymmetricity, and where we have increased the drain spacer length and reduced the source spacer length in the same amount. As we have increased the 2 nanometer of spacer, then we have reduced the 2 nanometer of spacer length. So for this case, we have considered drain spacer length as 10 nanometer, 12 nanometer, 14 nanometer, and then 16 nanometer. Further increment in the drain spacer is not showing much improvement in the drain current as well as in the parasitic capacitances, which we'll see in the further slides. So here we can see for the same amount of voltage, the drain current is very high in case of 3-fin structure as compared to the single fin structure, which is able to single fin is able to achieve 0.8 milliampere of current. At the same time, 3-fin structure with the same voltage is able to achieve around 0.25 milliampere of currents. So we can see here the gate to source capacitance with respect to the VGS in the left hand side and the gate to source capacitance with frequency in the right hand side. In the left hand side, we can see here that the gate to source capacitances initially start to increase when we increase the drain to source spacer, reduce gate to source spacer. Then in the single fin as well as in the 3-fin, the capacitance start to increase. But in case of 3-fin structure, we can see here for LDSP equal to 16 nanometer, there is a fall at the higher gate voltages. This is because when we start to increase the drain spacer and reduce the source spacer, there is increment in the inversion charges and the gate to source capacitance start to increase. But at some moment, the inversion charges will not increase, and we'll see the reduction in flux, and because of that, there will be the decrement in the charges, and that will reduce the gate to source capacitances. So the same reduction can be seen here with respect to the frequency also. So this is for the VDS 0.7, VGS 0.7, and we can see here the gate to source capacitance is quite low with respect to the frequency also, but at very high frequency there will be changes in the parasitic elements with respect to the frequency also. So they actually become the function of frequency at very high frequency. In the this slide, we can see the gate to drain capacitance with respect to VGS and gate to drain capacitance with respect to the frequency. So we have increased the gate to drain spacers, so the gate to drain capacitance will obviously reduce here, and we can see this in the results also, that for LDSP equal to 16 nanometer, it reduces drastically, although we cannot see much changes than single fin, but in the 3 fin it is quite reducing with the asymmetricity. So the impact can be seen in total parasitic capacitances, and the total parasitic capacitance for this higher asymmetricity, which is LDSP equal to 16 nanometer, we can see there is a fall in higher VGS for the total gate capacitance, because gate to source and gate to drain both are falling for the high drain spacer length and in the higher voltages. So the overall decrement can be seen in the total gate capacitances, and the same in the with respect to the frequency plot. So we can see here the transconductance is also increased in case of 3-fin structure as compared to the single fin structure. As we have already seen, for the same voltage there was quite high drain current in the 3-fin structure as when compared to the single fin structure. This overall impact can be seen in the cutoff frequency, which is in the right hand side of this slide. For the 3-fin structure, we have achieved very reduced parasitic capacitances in terms of CGF and CGD, and cutoff frequency is inversely proportional to the parasitic capacitances and directly proportional to the transconductance. That's why all these results are supporting to increase to achieve the very high cutoff frequency in case of spacer length when the drain spacer length is 16 nanometer. So we can achieve very high cutoff frequency, which is supporting for the 5G applications. We have also compared our results with the previously reported work. In 2005, when the channel length was 100 nanometer, then they are able to achieve 75.5 gigahertz of cutoff frequency. So the frequency here is given in the gigahertz, and transconductor is in the microsiemens, and capacitances are in the femtofarads. So for in the 2008, for the 60 nanometer of channel length, the cutoff frequency they have achieved is 100 gigahertz. For 14 nanometer in 2012 paper, it is 370 gigahertz, and in 2018 for 20 nanometer channel length, it is 250 gigahertz. In our case, for single fin and asymmetric structure, for optimized value of drain spacer length, which is 16 nanometer, and channel length is 20 nanometer, the frequency is 350 gigahertz, and for same dimension in 3-fin structure, we are able to achieve 479 gigahertz of cutoff frequency, which is quite high. And in the conclusion, we can say that the major challenges with the FinFET device are parasitic capacitances, and which are quite high for the 3-fin structure. And these can be resolved in the by introducing the small asymmetricity in the spacers. So with that asymmetricity, 3-fin structure is able to achieve around like 2 to 2.5 times increase in the drain current as compared to the single fin structure. Single fin structure shows the negligible changes with increase and decrease in the optimized spacer length, but 3-fin structure shows 44% of reduction in CGD for the asymmetric 3-fin structure with respect to the 3-fin symmetric structure. And also 3-fin structure is able to achieve 36% of improvement in FT, which is cutoff frequency, as compared to a single fin structure, even though it is having the higher parasitic capacitances. And thank you everyone. Thank you for your present sharing, and you are most welcome for the queries.
After this second interesting presentation on FETs, I would like to move on to the third presentation of the session, which is discussing on how good silicon oxide-based memristors can actually be. This paper is done and will be presented by researchers at Indian Institute of Technology, Ropar. Thank you.
Hello everyone. In this presentation, we will talk about how good silicon oxide-based memristor can be. I am Manishankar Yadav, PhD student from Electrical Engineering Department at Indian Institute of Technology, Ropar, Punjab, India, and other co-authors of this paper, Avinash Kumar Gupta, Kanupriya Vasne, and Brijesh Rawat. The outline of this presentation, which includes brief introduction of memristor devices, challenges with hafnium oxide and tantalum oxide memristors, device geometry and simulation methodology. Then I will be discussing the results and discussion, which includes IV characteristics of silicon oxide, hafnium oxide, and tantalum oxide memristors, thermal performance, comparison, writing time, constant comparison, readout, margin comparison, and conductance modulation comparison. Finally, I will conclude this presentation. So let's start with the memristor. Memristor is a simple two-terminal, three-dimensional device which consists MIM structure, that is a top electrode metallic and bottom electrode is metallic, and in between oxide layer is sandwich, that is insulating in nature. Also, the memristor is highly scalable and higher integration density, which makes it promising candidate for next generation non-volatile memory, logic, and brain-inspired computing application. The number of materials are exhibit resistance switching, such as metal oxides, silicon oxide, and two-dimensional materials, in which silicon oxide memristor present the most promising choice for the future non-volatile and neuromorphic computing due to its excellent properties, that is intrinsic electrical stability, and most importantly, it is low cost because the availability of silicon oxides and easy fabrication with existing CMOS technology line. So the most significant challenges faces the hafnium oxide and tantalum oxides for large scale array realization, that is integration issue with the CMOS fabrication process and considerably higher sneak path current. So left side we can see here, this is the 2x2 crossbar array architecture. This blue is the selected cell and current flowing through. This is the desired, and we can see this is a dotted red, that is the undesired current, known as a sneak path current, which is actually increases with increasing the crossbar array size. So this limits the our array size. So it is important to study the silicon oxide based memristor, which is having a several advantages over the hafnium oxide and tantalum oxide memristors. This is extremely compatible with CMOS fabrication process and having a higher band gap, about 8 electron volt, as compared to hafnium oxide is having about 5 electron volt and tantalum oxide is having about 4 electron volt. And it is also have a high temperature stability, which makes device performance robust with temperature. So we have considered for our study these three devices, silicon oxide memristor, hafnium oxide memristor, and tantalum oxide memristor. And for this silicon oxide based memristor having a top electrode gold and bottom electrode is titanium. For hafnium oxide, it is having a top electrode and bottom electrode both are titanium nitride. And for tantalum oxide, it is also having a top and bottom electrode palladium. And we have kept the oxide thickness is 40 nanometer to make a uniform performance comparison of these three devices. So in this regard, we have investigated the following key performance metrics for large-scale array realization. First one is the switching current, listening path current, on-off current ratio, switching time constant, readout margin, and last, conductance modulation. This is the multi-physics modeling approach we have adopted to simulate our device. So for silicon oxide based memristor, we have taken here that is a top electrode is a gold and bottom electrode is titanium, and this is the 40 nanometer oxide layer thickness, and we use the transport equation that is the continuity equation, current continuity equation, Fourier Joule heating equation, conductivity, Riff diffusion equation, solved in self-consistent way to get the IV characteristics. So here we can see the simulated IV characteristics with our model well matches with the experimental data. So this is the simulated IV characteristics. All these three devices at the 300 Kelvin temperature with a different voltage sweeping rate, and we can see this is the silicon oxide based memristor, hafnium oxide based memristor, and this is the tantalum oxide based memristor, in which our silicon oxide based memristor shows the higher on-off current ratio. We can see from here in the hafnium oxide, and this is the for tantalum oxide. So this is because of the higher energy band gap of silicon oxides, and it's significantly suppressed SNIC current, SNIC path current. Also, you can see the SNIC path current for silicon oxide is 0.43 microampere, which is significantly lower as compared to hafnium oxide, that is 12.09 microampere, and for tantalum oxide, that is 98.9 microampere. We have calculated this SNIC current using a P/2 writing scheme, which is the power efficient scheme for realization of large scale array. This is the thermal performance comparison. In figure A and B, we can see the V reset and V set, that is this reset voltage and set voltage is nearly constant for metal oxides, and significantly varying with temperature for the silicon oxide memristor. This is due to the silicon oxide is having a low thermal conductivity. And in figure C, we can see the switching current, which is decreases with temperature for hafnium oxide and tantalum oxide, which means this is showing the metallic nature of hafnium oxide and tantalum oxide. And in the case of the silicon oxide, it's increases with temperature. This shows the semiconducting nature of silicon oxide. And in figure D, we can see the off current, that is negligible change with the variation of temperature for all these three devices: silicon oxide, hafnium oxide, and tantalum oxide memristors. So transient response of memristor devices we have done with the voltage pulse with 500 nanosecond duration for silicon oxide, hafnium oxide, and tantalum oxide. So we found that silicon oxide shows the faster switching response as compared to hafnium and tantalum oxide memristors. This is because of top electrode near the higher temperature exhibit near the top electrode and the memory layer interface. Readout margin. We have calculated the readout margin using the readout margin formula. This is 1 minus IHRS. This is the current in high resistance state at V-rate plus N. N is the number of word line. So I leakage, this is the leakage current at V-rate by 2 divided by ILRS at V-rate. This ILRS is the low resistance current at V-rate. V-rate is equal to V reset we have chosen, and we multiply with 100 to get the percentage readout margin. So higher the readout margin percentage, we can accommodate more number of bits. So we can see for silicon, we are having higher readout margin, significantly high as compared to the hafnium oxide and tantalum oxide. This is due to the higher on-off current ratio of silicon oxide memristor. Conductance modulation comparison. This is first is shows the first our graph shows the silicon oxide memristor conductance modulation, and second one is the hafnium oxide memristor, and third one is the tantalum oxide memristor. So we can see here for case of silicon, the abrupt or we can say sharp change in the conductance modulation with the number of pulse. While in the case of hafnium and tantalum oxide, we can observe the gradual change. This is due to the generation of oxygen vacancy and self-heating. Self-heating results in more gap depletion gap, which makes the sharp change in the conductance of silicon oxide memristor. And this modulation in case of silicon oxide memristor is very high as compared to this. So this can be used for as a multi-bit element. So finally, we'll see the performance comparison of hafnium oxide and tantalum oxide with the silicon oxide memristor at the reset transition. So we'll see here the reset voltage for the silicon oxide is quite high as compared to hafnium oxide is 0.59 volt and tantalum oxide is 0.8 volt. And switching current is 147 microampere for silicon oxide. For hafnium oxide, it is 1.6 milliampere, and for tantalum oxide, it is 1.9 milliampere. So it is comparable that it is not that much low current as compared to hafnium and tantalum oxide. And a snake path current, we can see this changes drastically in case of this is suppressed drastically in case of silicon oxide memristor as compared to hafnium oxide and tantalum oxide. Tantalum oxide is even having about 100 microampere. It is very high, and hafnium oxide is also higher as compared to silicon oxide. So this is one good thing for realization of large-scale crossbar array. And we can see the on-off current ratio is also significantly high as compared to both the metal oxides. And inherent nonlinearity present in the silicon oxide memristor as compared to hafnium and tantalum oxide. And the writing time reduces in silicon oxide based memristors as compared to metal oxides. And bit capacity increases due to the higher on-off current ratio. You can see clearly here, silicon shows the 2 power 7, and hafnium is so the 2 power 5, and tantalum is lowest 2 power 4. So again, if we'll see all these key performance parameters, is desirable in case of silicon oxide memristors. So it is expected to be an excellent choice for large-scale crossbar memory, analog memory, and neuromorphic computing application. Thank you.
Thank you for the presentation and for this interested insight in the memristors. There is one question. Did you analyze the process variability on these three technologies?
No, actually, this is I will do for future studies. I haven't done this variability analysis.
And do you have any idea of how the stochasticity would be, like variation from cycle to cycle when compared to variation from device to device?
Actually,
if you have a feeling about that.
That is actually we have considered filamentary devices. So already in our calculation, we have considered a filament is there. So in stochastic, I feel that is a randomness of defects, or you can say. That one I am just studying that. So exactly I don't know, but
that would be very interesting result to see next year, maybe in this conference. That would be very interesting. Thank you. Thank you very much. And now we will move for our last presentation of the day, which is on the role of interface trap charges in the performance of monolayer and bilayer MOS2 based field effect transistors. This presentation and this paper, it's also presented by researchers in Indian Institute of Technology, Rapar. Thank you.
Hello everyone, myself Akhilesh Rawat, a research scholar from Indian Institute of Technology, Ropar. I'm going to present my work titled Role of Interface Trap Charges in the Performance of Monolayer and Bilayer MOS2 based Field Effect Transistors. Here is the outline for the presentation. First, we'll begin with the introduction about the 2D materials and how they help us in achieving devices at ultra-scale channel lengths. Thereby, we'll discuss the motivation behind the work. We'll look into the device specification and material parameters used for the simulation. Then we will discuss the modeling approach. Subsequently, we'll look into the results from our simulation, and finally the conclusion from our work. With the increasing demand for high speed and low power integrated circuit, 2D material has been seen as viable choice for ultra-scale CMOS devices. Some of the mostly explored 2D material include TMDC family, that includes material like MOS2, WS2, WSE2. Also, we have the graphene family, which includes material like graphene, silicene, germanium. These are zero bandgap material, which limits their usage in the devices. We also have black phosphorus family that includes material like black phosphorus, tin selenide, tin sulfide. Now, the 2D material possess properties, both electrical and mechanical, that give them the suitability for usage in the nanoelectronic devices. This includes atomic thickness, which helps in effectively increasing the electrostatic control of the device. Then it has higher carrier mobility. Certain materials like graphene in the 2D material family has a carrier mobility much higher than that of the silicon. Also, the pristine surface of a 2D material is free from the dangling bonds. Now, from the perspective of field effect transistor, TMDCs such as MOS2, WSE2 offer better prospects because of their decent energy gap. Even at a very low value of the off current, it is ensured that we get a higher value of on by off ratio. Also, the moderate effective mass effectively shields or effectively reduces the source to drain tunneling, and on the other hand also achieves higher carrier velocity. Now, the motivation behind this work. Among the 2D material family, especially TMDCs, the degree of readiness for MOS2 is much higher in analog and digital and integrated circuits development, as the recent fabrication processing allows for easy and large scale fabrication of single layer and multi-layer MOS2 sheets. Also, the recent research has demonstrated that the MOS2 based devices have excellent switching performance for ultra scale devices with higher on current of about 1 milliampere per micrometer and high on off ratio of around 10 to power 5. This can be seen from the figure 2a, that the on current is significantly high and we have a high on off ratio of about 10 to power 5. However, monolayer and multilayer MOS2 FETs suffer from substantial non-idealities because of the presence of high density of interface traps. The origin for these interface traps are broadly divided into 3 categories. It can be seen from the figure 2b that the type 1 type traps represent the defects and impurities in the MOS2 N-type channel due to the presence of sulfur vacancies. This type of traps are present in mechanically exfoliated and CVD deposited MOS2 sheets. Type 2 traps represent the traps in the high K dielectric oxide, or Then we have type 3 type traps. These are present because of strain induced externally in the MOS2 sheets. From the figure 2C, we can see that the interface trap density in the monolayer and high K dielectric interface is of the order of 10 to power 12, which is pretty high, in the energy range of -0.2 to 0.4 from the conduction band. Since trap charges in MOS2 is found to be the dominant source of potential fluctuation, these affect the device electrostatics. Therefore, it becomes crucial to investigate the impact of traps on device performance to guide for its optimization. These are the device specification and material parameters used in the simulation. We have used an intrinsic MOS2 channel material of length 12 nanometer with source and drain of dimension 20 nanometer. Al2O3 is used as an oxide which has a dielectric constant of 10. The effective masses are given as shown in the table. We have used the gate metal work function difference to get an off current of about 10 nanoampere per micrometer. The value of metal gate work function difference is -0.12 for monolayer MOS2 FET and -0.124 for bilayer MOS2. Now we'll discuss the modeling approach. Our simulation is based on the self-consistent solution of 2D Poisson's equation and NEGF formalism. The green function solution requires tight binding Hamiltonian. So we have considered a single band tight binding Hamiltonian considering 1D elementary cell along the width direction. The self energy is calculated through the Sancho-Rubio algorithm. Also, now the interface trap density is included in the 2D Poisson equation at certain specific energy levels. For the N-type FETs, it is the acceptor type traps that affect the IV characteristics. Therefore, we have included the doping concentration updation with these acceptor type trap charges. The updated concentration is fed back to the Poisson equation, which subsequently modifies the potential profile. Now, once the convergence criteria is met in this self-consistent loop, we calculate the current in the device through the Landauer's equation. Now we'll discuss the results from our simulation. First is the transfer characteristics for pristine monolayer and bilayer MOS2 FETs. It is shown in the figure the transfer characteristics for monolayer and bilayer MOS2 FETs obtained at a fixed off current of about 10 nanoampere per micrometer. It is seen from the figure that bilayer MOS2 FET has marginally higher current of about 2.7 milliampere per micrometer compared to monolayer FET current of about 2.1 milliampere per micrometer. The reason for this is slightly lower band gap for bilayer MOS2 FET. Also, the mobility value for bilayer MOS2 FET is about 1.5 times to that of monolayer MOS2. Now we'll discuss the impact of trap charges on the conduction band profile. So the conduction band energy shifts at low VGS is negligible as the trap charges are not charged completely. We can see from the figure that at higher value of VGS, the shift in EC, that is the conduction band energy, is significant because of the charging of these trap charge states. In between these, the value increases from as we proceed from 0.1 to 0.5 volts. We also see that the Gaussian trap distribution has higher change in the potential energy. Between monolayer and bilayer MOS2 FET, It is the MOS2 monolayer FET that undergoes more fluctuation. Now the impact of constant energy trap distribution. In this, we study the impact of constant energy trap distribution on the transfer characteristics for monolayer and bilayer MOS2 FET with the trap at -5 kT energy and 2 trap level at energy -5 kT and -10 kT from the conduction band for various values of the interface trap density DIT. It is seen that with increasing the trap density, drive current decreases substantially for both single and 2 trap level. In between MOS2 monolayer and bilayer FET, it is the monolayer FET which exhibits higher degree of degradation in the on current compared to the bilayer MOS2 FET. From the figure, it can be seen that significant degradation for trap density is seen for interface trap density of around 10 to power 12 centimeter square per centimeter square for value of VGS greater than 0.3. We'll now see the impact of Gaussian type trap distribution on the transfer characteristics for both monolayer and bilayer MOS2 FETs. The peak density of the Gaussian type trap distribution is 4 into 10 to power 12 per centimeter square, peaking at energy -5 kT from the conduction band. It is seen that the drive current is significantly higher for the case of Gaussian trap distribution in comparison to the fixed trap or constant energy trap distribution. As was the case with constant type trap distribution, it is seen that monolayer MOS2 FET exhibits higher degradation compared to bilayer MOS2 FETs. Also, severe degradation in the current value is seen for higher trap densities for VGS values greater than 0.2 volts. We now look at the digital performance metrics with trap charges. Now the impact of constant type trap distribution and Gaussian trap distribution on key device performance metrics such as on current, percentage current ion change, drain induced barrier lowering, and subthreshold slope as a function of trap density DIT is studied. We found that the on current decreases drastically for higher trap density. Subthreshold slope increases with increasing the trap density owing to the loss of electrostatic control. Bilayer MOS2 FET exhibits more robustness in the presence of interface traps. Now we conclude with the following points. It is seen that the bilayer MOS2 FET has been found to be more immune to trap charges, exhibiting lesser degradation in on current and the subthreshold slope. Gaussian type distributed charges severely degrades the drive current, posing serious challenges on device speed and power dissipation. Interface trap density below 1 into 10 to power 12 per centimeter square is needed to achieve higher current for a MOS2 FET. Further studies on interface trap charges on MOS2 FETs should focus on investigating the impact on circuits and exploring material and design ways to achieve more robust performance. Thank you.
Thank you for the presentation. What would you say are the main benefits of MOS2 FETs and the main disadvantages compared to classical FETs? I think you are muted. Could you unmute your microphone?
Okay, sorry. So yes, so it is the channel thickness actually that helps us greatly in achieving a shorter channel length, because the scale length in this case would be lesser. Also, since it has a stacked structure, so the dangling bonds would be less compared to your conventional material, say silicon or other materials.
And what would you say? Yeah, sorry, go ahead. You didn't finish.
So I was talking about the property in its oxide. So since the conventional material doesn't have that storage capacity in the oxide region, so it can be used basically in newer computer regimes like neuromorphic computing or the non-volatile memory. So that aspect is also there in this case.
That was exactly my second question.
Okay.
Thank you so much for the presentation and for your answers to my questions. Thank you everybody for participating in this session.